Hello students, in this video let us discuss the first Brillouin zone of a crystal and the condition for Bragg reflection based on crystal vibrations. So in the last video we already discussed about the crystal vibrations and the wave propagation through a crystal lattice. Now here in this video let us look into the first Brillouin zone of a crystal. For that, let us consider the ratio of displacements of two successive planes. So we have said that US plus 1 is the displacement of S plus 1 plane and US is the displacement of the S plane. So the relative displacement between these two planes will be given by US plus 1 is U into exponential I into S plus 1 into Ka, where K is the wave vector, divided by U into exponential I Ska, right? So this is equal to exponential I Ka. Now we know for an exponential function, e raised to I function, the independent values that this function can take lies in the range of minus pi to pi. So when Ka, the argument of this function, exponential I function, varies from minus pi to pi, we will have different independent values of this function. So if you put any other values that are greater than pi or lesser than minus pi, the function value that you obtain will be just the same as you obtain if the function Ka is within these limits. So since exponential Ika is a periodic function that repeats itself in the range of minus pi to pi, the values will be repeating periodically, and hence we can choose that the independent values this function can take will be obtained when Ka varies from minus pi to pi. So this actually covers this range of values of Ka from minus pi to plus pi actually covers the first Brillouin zone of the lattice, of the linear lattice. So when Ka varies from minus pi to pi, we can say that the K value varies from minus pi by a to plus pi by a. So divide throughout by a. You can say that the wave vector values which will give you an independent value of exponential Ika or the relative displacement will be obtained when the K function, the wave vector, varies from minus pi by a to plus pi by a, and this range of wave vector value actually constitute the first Brillouin zone of this crystal lattice. So what are the extremum values of this zone? The Kmax are given by plus or minus pi by a, the extremum values which actually constitute the edge of the first Brillouin zone. Now even if you have a wave vector value that is outside this first Brillouin zone, suppose you have a value of K that is outside these limits of minus pi by a and plus pi by a, even then you can change this wave vector to another wave vector K dash without affecting any physical significance of this wave vector, and this K dash can be included in this range. So I will show you how. For example, you have a wave vector K and this wave vector K is not in the range of minus pi by a to plus pi by a. It is outside this range, outside the first Brillouin zone. So then you can actually change this wave vector K vector by a factor of 2n pi by a, where n is an integer, without affecting the real physical significance of the wave vector. So if you have this K as an arbitrary value outside the first Brillouin zone, then you can define US plus 1 divided by US, which is equal to exponential Ika, and you can actually multiply and divide this by e raised to I 2n pi by a, right? So it is e raised to I 2 pi n into exponential I k a into e raised to minus I 2 pi n. I have divided and multiplied with e raised to I 2 pi by n. Now let me change this like e raised to I 2 pi n into exponential I k a minus I 2 pi by n. So this is equal to e raised to I 2 pi n into exponential I into k minus 2 n pi by a multiplied by a, right? So here instead of this k, we have obtained a new wave vector k dash, which is k minus 2n pi by a, and I can write this to be equal to, we know e raised to I 2n pi is 1, so this is 1 into exponential I into k dash a. So without affecting the physical significance of the wave vector, we can transform this k into a new wave vector k dash by adding or subtracting a term 2n pi by a. So in that way, even when the wave vector does not lie in the range of minus pi by a to plus pi by a, which is the first Brillouin zone, you can change that to another wave vector k dash which lies in the first Brillouin zone by adding or subtracting a term 2n pi by a. So we can effectively say that the first Brillouin zone is sufficient to explain the physical properties of wave propagation through a crystal, and any wave vector can be actually translated or transformed into a wave vector that is lying within the first Brillouin zone. Now let us consider the case when the wave vector value is equal to the extremum values. So we know at boundaries the maximum value of k is obtained, which is plus or minus pi by a, and let us write the displacement function us, which is equal to u into exponential isk. So if k is plus or minus pi by a, at the zone boundaries it will be equal to u into exponential I into s into pi by a into a, which is equal to u into exponential I s pi. So this is the displacement function, displacement of each of the planes, the s plane at the zone boundaries when wave vector is equal to plus or minus pi by a. Now we know this can have different values, either can have plus or minus 1 value depending on the value of s. So we can write this to be equal to, if u is a constant, we can write u into minus 1 whole raised to s, because exponential in pi is minus 1 whole raised to n. Depending on the value of n, we will have different, either plus or minus 1 value here as the answer, because exponential I 2n pi, 2 pi is 1, but 3 pi is minus 1, and so on. If we have an odd number here, we have minus 1 as the answer, and if we have an even number here, we have plus 1 as the answer. So this is the final answer to this function. us will be u into minus 1 whole raised to s. So this is the case when the wave vector is plus or minus pi by a. We have the displacement of the s plane to be equal to u into minus 1 whole raised to s. So surely this is not an oscillating function. So the subsequent planes, the alternate planes, will oscillate in opposite phases because us is plus or minus 1 depending on whether s is odd or even integer. For example, the second plane will be oscillating with us equal to u, and the third plane, for the third plane us will be equal to minus 1 whole cube, which is minus 1, so minus u, and so on. So different planes, the adjacent planes will be oscillating in opposite phases, and they will be actually constituting a standing wave and not a propagating wave. So because this the displacement of the s plane, as we can see here, this is not an oscillatory function, it is actually stuck there, kind of a standing wave that you see in a string. Just like that, these crystal vibrations actually do not propagate through the crystal lattice, and they will create a back and forth reflection within the crystal, which constitute a standing wave. So when Kmax equal to plus or minus, or K equal to Kmax, which is plus or minus pi by A, there is not an oscillatory solution. We will have a standing wave within the crystal, and each adjacent plane will be oscillating to the left and right, creating a standing wave. Now this particular condition of K value, when K equal to plus or minus pi by A, is the Bragg condition of reflection within a crystal. Just like the Bragg's condition that we discussed in the case of an X-ray falling over a crystal, this is the Bragg's condition. Just the same Bragg's condition even in the case of a vibration that is propagating through the crystal. So let us discuss about this condition. We generally know the Bragg's condition is given by 2d sin theta equal to n lambda. Here sin theta is the glancing angle. So since the wave propagates in a perpendicular direction to that of these planes, let us take the glancing angle to be equal to pi by 2. And we know the interplanar spacing is effectively the lattice constant A itself. So we have 2A into 1, which is equal to n into lambda into lambda, n into lambda. So 2A into 1 equal to n lambda is the Bragg's condition if a vibrating wave is propagating through the crystal. Now let us look at this condition here. We know K is equal to 2 pi by lambda, right? So the condition for the standing wave within a crystal in the case of a vibrating wave, so this can be rewritten as 2 pi by lambda is equal to plus or minus pi by A. Now I can rearrange these terms like lambda equal to 2A. So we can see that this condition of standing wave when the wave vector is equal to plus or minus pi by A is just the same as the Bragg's condition. So we can effectively substitute the Bragg's condition into the case of an oscillating wave or an oscillating wave that is propagating through the crystal. Now in the case of an electromagnetic wave, this wavelength lambda actually has a meaning. Lambda will be the wavelength of the propagating X-ray or the electromagnetic wave. In the case of the elastic wave that is propagating through the crystal, lambda is defined by the atoms that are constituting the lattice. For example, in this case you can see two different waves that are plotted here. This white curve and this dotted curve. Both the waves actually displaces the atoms by the same amount and same frequency. But you can see that the dashed curve is enough to plot this arrangement of atoms. You need not have a higher frequency wave in order to plot the positions of these atoms. So only the wavelengths that are longer than 2A, where A is the interatomic spacing, are needed to represent the motion of atoms while an elastic wave is propagating through a crystal. That is one another concept that we have to look into. So in this class we have looked into the concept of first Brillouin zone of a crystal based on the concept of propagation of elastic waves through the crystal, and we have obtained the condition of Bragg reflection, which is simply Kmax equal to plus or minus pi by A in the case of a crystal, and this is simply the Bragg's condition itself. I hope these concepts are clear for you. Thank you.